In this video, we're going to cover section 5.1, unit 5, still analytical trigonometry using fundamental identities. Lots of examples in this one. They're going to be pretty easy, hopefully, and pretty quick. Okay, just really quickly at the top, though, I do have a note that the Pythagorean identities, which are in your foldable, okay, those are sometimes going to be seen in a different form where you have a square root. It's called the radical form. So, for example, sine of theta would be equal to plus or minus the square root of 1 minus cosine squared theta. And likewise for tangent theta, where the sign, so the plus or the minus, depends on where your theta is located, okay? And again, this is from tab number 2. So it just, it's just using a little bit of algebra here. If you were to try to solve for, let's say, sine, you would move the cosine squared theta to the square root to get sine by itself. And that's kind of where this is coming from, okay? So with that in mind, let's go ahead and just jump right into an example. We're going to look at example number 1. Okay, if tangent of x is equal to 1 over 3, and cosine of x is less than 0, find the values of all 6 trigonometric functions. So we can do this two ways. We can actually just kind of draw the picture and see where it's at and find the missing values, or we can use one of the things we have up here, because I'm going to kind of do both just to kind of show you how they both go together, okay? So using what I have up here, the tangent of theta is equal to this, I can probably figure out what secant is going to be equal to if I solve for secant. So I'm going to do that. Okay, I'm going to say, since tangent of x is equal to 1/3, well, let's write it out so we can kind of see it all. So tangent of x is equal to 1 over 3. And according to this is equal to all of this, right? So the square root of secant squared theta minus 1. And what I'm going to do is I'm going to solve for theta using 1 over 3. Okay, so that's like the equation that I'm solving. So to do that, I would probably square both sides first. So we're pretending that we're ignoring the tangent x now. This is our equation. So I'm going to square both sides, and that would give me 1 over 9 is equal to all of this, secant squared theta minus 1, okay? You would then add 1 to both sides, so plus 1, let's see the other color here, plus 1 plus 1. So you're thinking over here, 1 over 9 plus 1, change that to a fraction, so 9 over 9, okay? And that would give us 10 over 9 plus 1 is 10, right? So 10 over 9 is equal to secant square theta, okay? And then we would square root this because, well, we want secant by itself, so square root this, which is going to give us, the square root of 10 is just the square root of 10. You really can't do anything with that. Square root of 9 is 3, and this would give us secant of theta. Okay, now the only thing we would need to check at this point would be the sign, because remember, this is plus or minus, depends where theta is located. So for this part, I would have to kind of go back over here and say, well, where is this going to be located? So a few things. It tells us that cosine of x is less than 0. So let's kind of do a little, just kind of a little analysis over here. Cosine of x is less than 0. And which quadrant does that happen? Which quadrants? If you don't remember, you can look at your foldable. I believe we have this in tab number 3. Okay, so if you look at tab number 3, it kind of shows you up here at the top where everything is positive, negative, and all that. So cosine is negative. We want it to be negative here in quadrant 3 and quadrant 2. So, and just think about, where is x negative? X is negative over here, so 2 and 3. So for cosine less than 0, we have quadrant 2 or quadrant 3, okay? For this one, tangent x equals 1/3, that means tangent is positive. So we also have to kind of analyze, let me kind of, this is like a side note here. We have to analyze where tangent of x is positive, because 1/3 is positive. So again, if you need to look at your foldable, look at it, and it tells us that tangent is positive in quadrant 1 and quadrant 3. So it's kind of like these two diagonals because remember it's y over x. So if the y over x are the same sign, they become positive. So that happens here and here. So we're thinking quadrant 1 and quadrant 3. You see what they have in common, so it looks like it's going to be in quadrant 3, okay? So in quadrant 3, we have to figure out, is secant going to be positive or negative? So this one is not in your foldable. I just included the main three, so sine, cosine, tangent. But secant and cosecant and cotangent are just the reciprocal of another function. So if you know that it's the reciprocal of something else, it's gonna follow the same sign pattern. So for an instance, we know that secant is the reciprocal of 1 over cosine, okay? And cosine in quadrant 3 is negative. So this one is negative. And there is one of the trig functions so far, secant, okay? But that's really all we need because now that we have secant, we can figure out the rest. Remember that all of our functions are defined by either x, y, or a combination of those two, and r, a combination of those two. So this right here tells us, I should probably put that over here. Well, it's okay. This tells us that remember, secant is the reciprocal of cosine, so it's kind of like r divided by x, right? So this will tell us that r equals the square root of 10 and x equals 3, okay? Probably shouldn't probably put an arrow or something because that looks kind of weird with an equal sign and a fraction. But yeah, so that's what we have. Don't worry about the negative, but the negative depends on which function we're using. So for secant, it happened to be negative because of where it's located, but for the other ones, it depends. Okay, so r is square root of 10, x is 3, and y is, we already have it, it's up here. Remember, tangent is y over x, so y is just equal to 1. And we have all of our, well, let's just get rid of that. Ugh, let's just get rid of that. We'll just do equals, I guess. My bad. So r equals this, x equals that, y equals that. But I just wanted to show you that secant is r over x. That's how I was able to get this one, okay? Now, another way you could have done this, and I do want to show it real quickly because it might be easier for you, okay? This method right here was using the identity that we have up here. Another way you could have done this is once you figured out where this goes, okay, you could have drawn the triangle. So we know it's in quadrant 3 somewhere. And we know that since this is tangent, and here's our theta. Since this is tangent, we're thinking opposite over adjacent or y over x. So the y value is 1, okay, opposite, and the adjacent is 3. So using Pythagorean theorem, you would have gotten square root of 10 for your r. Pretty cool, huh? All right, but same results. Okay, so let's go ahead and find the rest of them. Now that we have secant, we need to find well the rest. Okay, so let's go ahead and do I don't know, let's do cosine because cosine is just the reciprocal of this one, right? So cosine is equal to 1 over secant of theta, which means all I have to do is flip this right here. So it's going to be negative 3 over the square root of 10, which we're not really allowed to have. So let's fix it. That's going to be negative 3 square root of 10 over 10. And yeah, that's it for that one. Okay, let's move on. Oh, and yeah, it is negative because, again, it's in quadrant 3. So over here, cosine's negative. Let's do sine. Let's try sine. Sine theta. So sine theta is going to be y over r. You need to remind yourself that's fine. And our y is 1. So 1 divided by r is square root of 10. So if we fix this, we get square root of 10 over 10. If you don't know what I'm doing from here to here, again, come in and see me for tutoring and I will show you, okay? Now we got to figure out is sine negative or positive in quadrant 3. If I remember right, y is negative here, so this is also going to be negative. Okay, so far we have 1, 2, 3. We need cotangent and cosecant, I believe. So let's go ahead and do those ones. Let's do cosecant next because cosecant is just the reciprocal of this one. It's just r over y. Okay, so I got to flip this now. So I'm going to say negative 10 over, and again, this is negative also because remember they're reciprocals, these two. So this one's negative there, this is negative there also. Okay, so negative 10 over the square root of 10, okay, which would give us, let's see, negative 10. Bring this guy up. We're left with the 10 on the bottom. The 10s give us a 1, so we have negative square root of 10 for cosecant. Okay. And last but not least, we have cotangent of theta. And this one's going to be the easiest one of all because cotangent of theta is the reciprocal of of tangent. It's just 1 over tangent of theta. And tangent of theta was equal to 1/3. That was what they gave us up here. So all I got to do is flip it, 3 over 1, which is just 3. And we ask ourselves, is cotangent going to be negative or positive in quadrant 3? Well, I mean, this is the same as r over y, okay? I'm sorry, not that. What am I saying? As x over y. There we go. And since both x and y are negative in quadrant 3, two negatives make a positive. And again, because this is the reciprocal of tangent, it's going to use the same signs as tangent. So that is it. These are the 5. I should probably put them all there. These 4 and this one over here. Okay. Okay, to simplify the expression, cosine square of x times cosecant x minus cosecant x. So we're going to just kind of factor here. We're going to say, what do these two have in common? They both have a cosecant, so I'm going to pull that out, kind of like my greatest common factor. Okay, and what am I left with? Well, I'm left with cosine square of x minus 1, because that's still a 1. Okay, and this is kind of sort of well, you know what? Let me show you. Let me just show you how to get this. So this looks a little bit familiar. If you look back at our tab 2, the identities, okay, you will see that we have one that has a cosine square in it. This one, okay, and I remember I wrote some optional ones here. I said if you move it over, we get 1 minus sine or 1 minus cosine square. So we kind of have that. We have it backwards though, right? We have cosine square of x minus 1. So we kind of have to kind of play with that a little bit. We want it to look like this, 1 minus cosine square. So what I'm going to do is I'm going to pull a negative out of here. Okay, I'm going to say if I take out a negative, so we're going to divide out a negative 1. Okay, so basically you're kind of thinking divided by negative 1, divided by negative 1. Okay, and then what that's going to do is we're going to have a negative out here in the front, so negative cosecant of x. And in here, we're left with negative cosine square x plus 1, right? And that still looks a little weird. Remember, I wanted 1 minus, but this is the same as that. All I have to do is fix it. So this is the same as if I put the 1 in front, 1 minus cosine square of x. That is the exact same thing. I'm just bringing everything else down. And this one is the same as sine square. So now I can do negative cosecant x. I say cosine when I mean cosecant. Just look at what I'm writing. I tend to kind of mix those up when I'm saying them, but they sound the same. That's why. So cosecant of x, and then we have on the inside sine square x now. So I'm using my identities, okay? And then check this out. We know that cosecant is the same as 1 over sine of x, the reciprocal, yeah? So what I'm going to do next, I'm going to bring this down right here. Remember, these are being multiplied. When you have something like this, you can kind of get rid of one of the signs because you have two up here, sine square x and then sine down here. So we can kind of cross one out and we're left with negative 1 times one of the signs up here. So negative sine x. And that is our simplified form of this problem. Okay? If I lost you here, this is the same as sine of x times sine of x. That's how I was able to cross out one of them, okay? All right, that's it for that one. Moving on, next one. So this one has a little bit of more the unfoiling that you guys like to call it. Let's look at letter A first. Okay, so letter A kind of has it looks like the one we kind of did earlier, right? Where we know that this is going to be sine square x or sine square theta, but we want to factor completely. So I'm actually going to use my difference of squares for this one. Difference of squares. You forgot what that is. It's basically a square minus b square equals a minus b, a plus b. So it's like you have these perfect squares. This is a side note. Okay, this is just in case you don't remember, so you don't have to write it down if you do. If you have perfect squares, you can separate them into two binomials where they have, the square root of each one, plus or minus or plus. So we can see here that we do kind of have that going on here. We know that the square root of, I'll do this, the square root of 1 is 1, okay? We'll put our symbols minus and plus or plus and minus. Doesn't matter which order you put it in. The square root of cosine square theta, well, it's just cosine. Cosine theta, cosine theta. And that's it. Let me write it a little bit nicer. It looks a little bit crowded. So 1 minus cosine of theta times 1 plus cosine of theta. And that's it. This is our factored form using difference of squares for this one. Pretty easy, hopefully. Let's look at the one right next to it. This one's going to require a little bit of thought, and we've already kind of sort of done some similar to this one, but we're going to kind of go over it a little bit more officially here to see if you can kind of pick it up, okay? For these ones, you'll notice that we kind of have a trinomial pattern. You have something squared, and then something in the middle, the same something, and then a constant. So you're thinking trinomial factoring for this one. Trinomial factoring. Again, kind of like unfoiling, where you're trying to find two binomials that if you multiply them will give this back to you. Okay, so what I'm going to do to kind of make this a little bit easier is I'm going to say this is similar to the following. 2x squared minus 7x plus 6. Okay, so I'm going to replace my cosecant squares with just regular old-fashioned x's, and I'm going to factor this, okay? So let's factor this. To factor this, we can do several methods. There's slide and divide, there's the guess and check. I'm going to just do guess and check for time purposes. So I know that 2x has to go in one of them, x has to go in the other, because 2x times x is 2x squared. For 6, I know I can do 6 times 1 or 3 times 2. And I somehow have to get a -7 in the middle. So they're probably both going to be negative. Okay. So negative, negative. You have to be a little careful here because not only does it have to multiply to the middle, I'm sorry, to the end, but it has to, you have to consider this too. So whatever numbers we choose have to multiply to my 6 and give me my 2 also as part of the FOIL, okay? So that's why the slide and divide method works right away, but we're just going to do the check. So I'm going to use 3. I think 6 and 1 is too big, so I'm going to use 3 and 2. I put a 3 right here, okay? That would be 2 times 3, which would be 6, right? And then we put our 2 over here, which would give me 2. So 6 and 2 is going to be too big. It's going to be 8, right? Let's try to put the 3 here and the 2 over here. So let's see what that would look like. 2 times 2, so 2x times 2 is going to give us negative 4x, okay? And then negative 3 times x would be negative 3x. And if we add them, we get that negative 7x that we wanted. That's how I do my quick checks here. You check the middle terms and say, are they going to add up to the middle? Okay, and it does. So this looks like it's going to work. Okay, so this would be our factors for this particular example. Okay, because again, these two multiply will give me that 6 at the end. So what I'm going to do now is I'm going to go ahead and do the original problem because that's what we're trying to do. And instead of using x's, I'm going to use the cosecant because it's the same concept, really. So we're going to have, let's see, 2 cosecant of theta, and then cosecant of theta. And then I'm trying to find a number that will multiply to 6 and add up to -7. So I already kind of found that over here, right? So -3 minus 2, and that should work. This should be my answer. But if you're not sure, what you can do is quickly FOIL it. We're going to do it super fast. So the 2 cosine, I'm sorry, cosecant, 2 cosecant theta times cosecant theta is 2 cosecant theta squared. 2 cosecant theta times -2 is -4 cosecant, I keep going around cosine, cosecant theta. The inside, -3 cosecant theta, and the last, +6. So these two combined give me that -7 that I wanted. Bring everything else down. And what do you know? It's the same kind of factoring that we've seen all our lives. Well, all of our high school lives, maybe. That's it. That is the answer for this one. So hopefully that wasn't too scary. Okay. So for this one, it's kind of like the one before, but we don't have the same terms, right? We have a secant squared x and we have a tangent x. So what I'm going to do is I know that these two are kind of related. That's you kind of heard me getting my foldable. So let's look at our identities and see how they're related. We have, let's see. That's secant squared theta, and remember this is the one I added. You probably, if you don't have it, that's fine. You can get it from the original, from this. 1 plus tangent squared theta equals this. So secant squared theta, oh, actually, it's given. This is what we're looking for right here. Secant squared theta is equal to 1 plus tangent squared theta. I had to get a better paper to make this foldable easier to read. But you get the idea. So this one is equal to 1 plus tangent squared theta. So I'm going to first replace this with 1 plus tangent square. Oh, and they're using x, so x. Okay. Bring everything else down. So plus 3 tangent of x plus 1. Okay, and we're just going to rearrange this to make it look like a kind of like the one before, right? Like a trinomial here. So we're going to start with our tangent because that's the square one. So tangent square x. Then we're going to do the middle term, so plus 3 tangent x. And then we have 1 plus 1 is 2. And look, we now have a similar thing to what we did before. If you have a hard time with this, if this looks scary to you, then do what we did in the other one. Break it down and do something similar. Okay, do the x's instead. So here's my similar. Well, actually, I'll do this after. Let's do this one first, and I'll show you how it relates to this one. So you can kind of work backwards. So I know that to get tangent square, we have to have tangent in each one. Okay. 2 is only has a few factors, 2 times 1, yeah? And since both of these are positive, I know it's going to be plus 1 and plus 2. And that should give me my answer, yeah? Let's see if it works with the similar pattern. So if I used x's, it'd be x squared plus 3x plus 2. Okay, basically replace the tangent with just an x. And if I try to factor this, you can see right away that the factors are just x plus 1, x plus 2. And if we compare it to this, tangent of x plus 1, tangent of x plus 2. So we are good to go with this one as well. Getting a little bit happy face crazy here with all these right answers. Okay, so yeah, that's it. That's the end of that one. Moving on. Number 5, and we're almost done, guys. Number 5. Number 5, I was not going to do because we kind of already did one similar to this, but you know, it's okay to do a little bit more practice. So let's do number 5. This one says rewrite so that this is not in fractional form. So we have cosine squared theta over 1 minus sine theta. What I'm going to do is I'm going to use what we call the monomial denominator. And we've done this already before, so hopefully this one is not too new for you. I'm going to multiply times kind of the opposite of this. So 1 plus sine theta, 1 plus, oh, I put 2 pluses there, didn't I? 1 plus sine theta. And I'm allowed to do this because, again, this is just saying like times 1. So let's do that. We're going to distribute which gives us cosine squared theta times 1 is cosine squared theta. Okay? Cosine squared theta times sine is going to give us plus cosine squared theta times sine of theta, okay, all over, well, the bottom is just going to be, it's kind of like the one we saw before. You're going to FOIL this, and when you FOIL it, you get 1. The middle terms will give us a 0, so make sure that this is a plus, okay? Don't get confused. The middle terms will be a 0, so the last term is going to be negative sine theta times positive sine theta, which is minus sine square theta. Okay, and we're kind of sort of almost done, but we can go further, right? And plus we have to have this, we don't want a fraction, so we gotta keep going. So from here, I know that this bottom one, 1 minus sine squared theta, again, going back to our identities, okay, Pythagorean identities, if I move the sine squared theta over, you get this one. So it's cosine squared theta, yeah? So let's replace that. We'll have cosine of square theta plus cosine square theta times sine theta all over, I'm replacing this one right now with cosine square theta. And maybe some of you can kind of see what's going to happen here, but at this point, you can basically factor out a cosine square theta from everything. And if that's a little bit too much for you, you can also expand the fraction. So we would have cosine square theta over cosine square theta, so these two, plus cosine square theta times sine theta over cosine square theta. So I'm just, breaking it up into two fractions. This is going to give us a 1. This is going to be gone, and we're just left with sine. So it looks like our answer is going to be 1 plus sine of theta. And that is it. That's the answer for this one. Pretty self-explanatory. Okay, 2 more examples, super quick. We have a trigonometric substitution example where you're basically just substituting something for something else. Let's just jump right into it. Okay, we have use the substitution x equals 3 sine theta, where theta is between 0 and pi half, so you're thinking quadrant 1, okay, to write the square root of 9 minus x squared as a trigonometric function of theta. So what are we doing? We're taking this value and we're going to plug it into x. That's it. And we're just going to simplify. So let's do that. We have the square root of 9 minus x squared. Okay, and I'm going to substitute. So I'm going to get 9 minus, inside the x, I'm going to go ahead and put all this, 3 sine theta squared. Okay, and if we kind of simplify this, we would get the square root of 9 minus, you're going to distribute the square to both the 3 and the sine, which would give us 9, because 3 squared is 9, and then sine square theta. Okay, from there we can factor out a 9, like so. 1 minus sine square theta, parentheses, I keep forgetting that, because you can take a 9 out from both this term and this term. And then this right here should look familiar. It's, again, I'm not going to show the foldable. Hopefully you know by now, but you can look at your foldable if you need to. That is the same as cosine square theta. So this is now 9, square root of 9 times cosine square theta. Okay, and since we are taking the square root of this, we can, and it's multiplication, okay, we're not adding, subtracting. If it was adding, subtracting, whole different story, but we are multiplying, so we can do this, square root of 9 times the square root of cosine square theta, and you'll notice that right away, this is going to be equal to 3, because square root of 9 is 3, and my cosine square theta is going to become just cosine theta. And we use the positive one because, well, it told us up here that theta is in quadrant 1. So everything is positive in quadrant 1, okay? And yeah, that's it for that one. Last one. We're almost there. So example number 7, and you're going to think, oh my gosh, why are we doing logarithms? Because they do come up, okay? And this one's actually pretty simple, I promise. It's not that bad. will be done in like maybe less than 2 minutes. So rewrite ln of secant x plus ln of sine x as a single logarithm and simplify. So we do have to kind of go back a little bit to our logarithmic knowledge, I should say. And we're going to use the rules of logs, in this case, natural log, to make this work. Okay, so I remember, and if you don't remember, I'm going to remind you, okay, that when you are adding logarithms that have the same base, in this case, these are both natural logs, so they do have the same base, we can condense them to a single logarithm. We can do that by, since we're adding, we end up multiplying. So secant of x times sine of x. So we are allowed to do that based on the rules of logarithms, okay? And from here, it's just a matter of simplifying this. So we're going to go ahead and do that. I know that secant of x is, what is that? 1 over cosine of x. Remember, this is the reciprocal of that. Well, it's equal to, yeah, the reciprocal of cosine. So it's equal to 1 over cosine times sine of x. Okay, I'm going to write this just so it looks a little bit nicer. So ln of, we'll put the sign on top because sine of x times 1 is just sine of x. A little bit crooked here. Over cosine of x. And hopefully you know this one. This is a quotient identity. You can look in your foldable if you need to. But sine over cosine is just tangent of x. And that is it for this example and for this video. As always, if you need anything, more explanations, just let me know.